So let's go through some applications of average rate of change, keep tying back to that a bit, but then also bringing this idea of instantaneous rate of change in here. So what we'll do is we'll look through some applications together, and then with that, let's get a formal definition of instantaneous rate of change. It's just kind of nice to work with a tangible example first before we kind of get into all this notation with limits that we're going to be seeing. So this first scenario, we have the function h of t, which is defined below as 10 times the square root of t, which gives the height of a hot air balloon after t seconds. And we want to find the average rate of change from, and let's change this up, from t equals 1 to t equals 10. It said t equals 0. Let's switch it to t equals 10. So we're going to see is basically on average, how did the height change after 1 second it had passed to 10 seconds passing. All right, so what we need is two coordinates. So we want to look at what happens if we plug in 1, and then what happens if we plug in 10. So h of 1 would be 10 times the square root of 1, which is just equal to 10. So we have the coordinate 1, 10, and then h of 10 would be 10 times the square root of 10, which we'll just leave it in that format there, 10 times the square root of 10. All right, so we're going to set up, we're just finding average rate of change. So let's take the difference in y values. So 10 root 10 minus 10 over the difference in x values, so 10 minus 1. And then with that, let's just go to a calculator. So I'm going to go to my Desmos scientific calculator. Let's separate the numerator and denominator. So we're going to have 10 square root 10 minus 10 over 10 minus 1. And we're seeing a 2.40. So now that we have some units here, let's talk about how we could put this into a sentence. So for units with slope, we always talk about the change in y over change in x. And with that, the units match up. So y is measuring, or rather the output is measuring the height of the air balloon. So the height is in, they don't tell us the measurement for height. Let's say it's yards. I'm totally making that up. Maybe it's meters. Let's go with meters. Okay, so the height is in meters, and then over, and then the units for our input is in seconds. So this is like meters per second. So what we could see is from 1 to 10 seconds, the hot air balloon, or let's say the height of the hot air balloon, and since this is positive, that height was increasing. So the height of the hot air balloon increased by 2.4 meters per second on average. So that was the average increase we were seeing across that moment in time. So there's our average rate of change. Now let's talk about average rate of change a little bit more, and then we'll throw in some instantaneous rate of change. So right here, we have a function d of t, which represents the temperature in Denver, Colorado, measured in degrees Fahrenheit, and that's t hours after midnight. So t is in hours, d of t is in degrees Fahrenheit. And what we have are these different times. So 6 a.m., 7 a.m., 9 a.m., 11 a.m., 15 hours after midnight would be 3 p.m. And then our different temperatures, 68 degrees, 69, 77, 82, 71. Kind of makes sense. The temperature's increasing as we get closer to noon, and then it starts decreasing. All right, find the average rate of change in temperature between 6 a.m. and 3 p.m. So we have the coordinate 668, and 3 p.m. would line up with 15, which had an output of 71. So this is average rate of change across two coordinates, so I'd do 71 minus 68 over 15 minus 6, which is gonna be 1/3. So on average, let's see, we're seeing an increase of 1/3 degree Fahrenheit per hour is how those units would go. Taking our output units, which was the temperature, divided by input units, which was hours. Okay, when did the temperature change at a faster rate? 9 a.m. to 11 a.m. or 11 a.m. to 3 p.m. So we're going to do two calculations. 9 a.m., so we had 9 and 77, and then 11 a.m. was 11 and 82. So average rate of change, we'll do 82 minus 77 over 11 minus 9, and that's going to be 2.5 degrees Fahrenheit per hour. And that was an increase in temperature over that amount of time. Let's see, 11 a.m., so we have 1182 to 3 p.m., which was the 1571. So average rate of change, we'll have 71 minus 82 over 15 minus 11, and that should be a negative 2.75 degrees Fahrenheit per hour. In this case, we're seeing a decrease in temperature, so it's cooling off that part of the day. Now we're just interested in like steeper change. It doesn't say like getting hotter or getting colder. So increasing and decreasing doesn't matter so much. So with that, we're really focused on the absolute value here of just like what's the larger number, disregarding any idea of positive or negative. And with that, it's going to be that 11 a.m. to 3 p.m. with a 2.75, because that 2.5 is smaller. So with the 2.75, that tells me that 11 a.m. to 3 p.m. change was more extreme. Okay, then estimate the instantaneous rate of change in temperature at 9 a.m. Now this is going to be a little tricky with the table that we have. In the next example, we'll get closer to what we'll do more often when we have the function available. But what's going to happen here is if I want this instantaneous rate of change in temperature at 9 a.m., so I'm really focusing on 9 a.m., it's going to be this idea of zooming in and thinking about how is temperature changing around 9 a.m., as close as we can possibly get, which would be the information at 7 a.m. and the information at 11 a.m. So there's a few different ways we could go about this. We could look kind of across like 7 to 11, but that's quite a big distance there. What we could also do is just look 7 to 9 and then 9 to 11 and average those together. Few different ways, but overall we want to get this idea of rate of change around 9. I'm going to go ahead with just one calculation going from 7 to 11 to see how are we seeing what's this average rate of change across 9 o'clock. So what I'm doing here is I'm just grabbing the smallest interval that contains 9 a.m. Just gonna make a note of that so you know why. So I'm gonna go 7 a.m. to 11 a.m. So our two coordinates, we have 769 and 1182. So the average rate of change is going to be 82 minus 69 over 11 minus 7, and we're seeing a 3.25. And that's a increase of 3.25 degrees Fahrenheit per hour. So it's not the most accurate of calculations, but it's the best we can do with the table of values. Table's going to be restricting because we don't have a lot of information, whereas with a graph, we can see exactly what's happening around that function. And then even better is having the function itself, which we're going to have in this next example. And what I'll do is show you how we can work with our function there if we have the actual function to plug in numbers into. Okay, so we're going to let f of x equal x plus 2 quantity squared. And what we're going to do is put these in the order from least to greatest. So we have 2 average rates of change and then 2 instantaneous rates of change. Now what we could do is we could estimate this with a graph. Then that's what we're going to do. Sorry, I was thinking of other ways we could do it, but not until we get some limit definitions and derivatives, which we'll be talking about next week. All right, so average rates of change, had a lot of practice with. So this first one, I'm looking from -5 to +1. So I'm going to want 2 coordinates. What happens when x equals -5? What happens when x is +1? So if I plug in -5, -5 plus 2 will be -3. Square it, and that'll be a 9. If I plug in +1, 1 plus 2 squared is 9. So with that, we are going to have an average rate of change, which maybe you already see with those y values being the same. We're going to have a numerator of 0 there, 1 minus a -5 in the denominator, so 0 over 6, which is just 0. So this has an average rate of change of 0. In fact, let me grab a picture of our graph here. So I'm going to go ahead and graph x plus 2 squared into Desmos. I'm just going to grab a snippet of it so I can draw on top. I'm going to need to see a little bit further above because I want to see the output of 9. All right, something like that should be good. Okay, so if I get this picture, what we just did is that average rate of change, and that's our secant line. So if we have 2 coordinates on our function, and in this case, our 2 coordinates is -5, +9, and 1, +9. So if we graph that, what we're getting is a horizontal line, which has a slope of 0. So that's why our average rate of change is 0, is because on average, there wasn't any change. Basically, our function evened out in terms of how much decreased. It then increased that same amount, so on average, there was no change. All right, let's do the same thing with -3 to +4. So x being -3, let's see, -3 plus 2 is a -1. Square that, and we'll have a +1. +4, we'll have 4 plus 2 is 6. Squared is 36. This is going to be off of my graph here, but we could start to get an idea of what this secant line would look like. -3, +1, and then 436 is way out here. So if I kind of sketch that secant line, this is going to be a very big positive value is what I'm expecting, and we could actually calculate it. So average rate of change will have 36 minus 1 over 4 minus -3. So 35 over 7, which is a +5. So big positive slope there. All right, instantaneous rate of change gets a little trickier. So what we're gonna do is let's see, x equals -3. So what I'm going to do is go to -3, +1. And what I want to do is try to sketch a secant line. Or sorry, a tangent line, because I have one coordinate here. So this is where it would be like taking a ruler or a straight edge of some sort and trying to kind of bump it up. Like I would zoom in as close as I could. In fact, while I have Desmos open, it's like if I look at -3, +1, if I zoom in and in and in and in, if I keep zooming in, even though there is curvature to the graph, if I zoom in enough, it looks linear. And that's the idea that we're getting at. I want to know what the slope is of this line that is infinitely zoomed in around this point, because I want to know this graph behavior, this rate of change right here. Let's see, it kind of looks like a -2 is coming through. So like the squares that are occurring, the units are a bit off here, but it looks like it would come out to like, if you have 1 point decrease by 2, go to the right one, that would be our slope there. So this is where it's a benefit to have the actual function itself, because we could do this in Desmos of zooming in and in and in and in and in and getting an idea of how is our graph changing. So with that, and I could try to kind of match up here, and it should come out to something that looks like about -2. And if you're a little off, that's completely fine with where we're at right now, but that average rate of, or sorry, instantaneous rate of change, IROC, we're going to say is about -2. Now, because I've taken calculus before, I know for a fact it is -2 with calculations we could do, but for now we're just kind of working visually with it. All right, instantaneous rate of change of x equals 4. So I'm going to go back to Desmos here. This one's going to be a bit tricky, but again, I know what the number is because of good old calculus, which we'll have later on. So if I get to the coordinate 436, which is going to be way up here. In fact, let me label the coordinate 436. So there's my coordinate on the function, and let's start zooming in real close as we possibly can. And what we could get from this is it's increasing. It's very steep right here. This is going to be a very positive number, and this is going to be hard to estimate. We could maybe kind of count and see, like if we go to the right one, see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I know for a fact that it's +12, but basically we could get an idea that it's definitely more than 5. Our whole goal is just putting these values in order, but what we would have here, from that I could get the estimate of 11. I know that it's actually 12, but the idea is that it's positive and very, very steep. So in terms of putting these in order, I kind of think of having a number line with 0 in the middle. Let's see, graph number 1 would be at 0. Graph number 2, or sorry, the rate of change of number 2, which we calculated as 5, is like positive, so it's to the right of number 1. Number 3 is negative, so that would be to the left of our number 1 graph. And then number 4 would be to the right of all of these, since it's the most positive. So in terms of going in order, it would go 3, 1, 2, 4.